In this video, we're going to cover section 5.6 of the text about bias. So we're finally going to formally define bias, okay? So suppose that we have an estimator, theta hat, of a true value of a parameter, theta. So oftentimes, the parameter we've been interested in has been the mean, mu, of a population, and we've estimated it with the sample mean, x bar, okay? So x bar would play the role of the estimator, and the true value of the parameter is theta. In fact, I'd like the word parameter to be in there. Now, if we happen to know the value of theta, and we do some kind of simulation to get lots of things for the estimator, maybe we do permutation, maybe we do bootstrapping, anyway, we create a sample distribution of x bar, then the bias of our estimator is the expected value of the estimator, the mean of the estimator sample distribution, minus the true value of the parameter, okay? That's the bias. So that tells you your simulation, if your bias is like 0.8, it tells you your simulation is biased to giving a mean that's higher than the true population averages, okay? All right, well, oftentimes we don't know the true population parameter, its mean, its correlation coefficient, whatever it is. So we have to try and sort of estimate what this bias is. So let's look at it in bootstrapping. So in bootstrapping, we calculate our theta hat, our estimator, via a statistic from our one sample that we've been given, okay? We then calculate 10 to the fourth or 10 to the fifth values of theta hat, which I'm going to call theta hat stars, via resampling with replacement. And I create my sampling distribution via those theta hat stars, okay? And then the expected value of those theta hat stars is the mean of the bootstrap distribution of theta hat, okay? That allows us to define the bootstrap estimate of bias. So I would estimate the bias to be the bias of bootstrap of theta hat star, which is the mean of my sampling distribution of theta hat, so the expected value of theta hat star, minus theta hat. That was the statistic from that one sample we began with. So that would be my estimate of bias, okay? Now, if your bias calculation happens to give you 0, then we say the estimator is unbiased. And let's look at an example of a very nice and common unbiased estimator we've been using all the time. And I'll be going back up to this definition of bias. So suppose I have x1 through xn, a random sample from a distribution with mean mu, all right? So that mean is known. I guess that population mean is known. The statistic I'm going to use to estimate mu is the sample mean, x bar. So x1 up through xn added together divided by n. And I've done this computation before, but if I calculate the expected value of x bar, I can do it with theory, right? I can drag the 1 over n out. I can apply the expected value to each piece, and each expected value, since it was randomly sampled from this distribution, each expected value of xi is mu. So I've got n copies of mu divided by m is just mu. So the bias of x bar is the expected value of x bar minus the population mean mu. And I just calculated the expected value of x bar to be mu. So I have mu minus mu, which equals 0. So great, x bar is an unbiased estimator of mu. That's important. Great. So even if I don't know the population or distribution mean, I have just proven that x bar, a sample mean, is an unbiased estimator of the population mean. Cool. By the way, pause, copy, play. All right. So x bar is an unbiased estimator of the population mean. But if I start doing funky stuff with sample means, I don't necessarily preserve that unbiased aspect of it. So if I had two samples, an X sample and a Y sample from two different populations, the ratio X bar divided by a Y bar need not be an unbiased estimator of the mean of population X divided by the mean of population Y. And the result is, the reasoning behind that is simply because of problems with division. If if the mean of population Y happens to be small, close to zero, dividing by a number close to zero can very quickly get very large. So you're introducing a lot of potential magnification in this test statistic X bar divided by Y bar, and it doesn't preserve unbiasedness, okay? All right, now bias is an actual measurement, a measurement of distance. And so if your bias between your estimator and your true parameter is like 0.2, it kind of matters about 0.2 out of what? So what if your parameter is your population mean and it's 1,000? If your bias is 0.2 for a mean of 1,000 versus your bias is 0.2 over a mean of 0, that's radically different. Like being a bias of 0.2 with a mean of 1,000, that's pretty close. You know, that's not either side of 1,000 very far. But if your mean is 0 and it's 0.2, well, then now it's a bit more significant, that distance away from the true mean, okay? So we try and standardize bias. So if I've got an estimator theta hat, I can often standardize its bias by taking the bias of theta hat and divide it by the standard error of theta hat, okay? Now remember, when we do bootstrapping or permutation testing, we can get the standard error of that sampling distribution from R. So as a general rule of thumb, if this standardized measure, if its absolute value is greater than or equal to 0.02, 2%, then we basically start to get nervous about the bias. We feel the bias could have a substantial impact on the accuracy of the bootstrap confidence interval, okay? So we become concerned that our simulation is not doing a very good job of capturing the truth, okay? So it's sort of a 2% threshold. Okay. Let's look at an example now. All right, last panel, we will be delving into some R here. Okay, so this is example 5.7 from the text. And I've got some things to fill in down here, but basically pause, copy, play. All right, so in example 5.7, we're running a longitudinal study over time about high blood pressure versus low blood pressure in men. Okay, so I don't know how long the study lasts, but it may last for 10 years. And at the end of the 10 years, they found that 55 of the 3,338 high blood pressure men died of cardiovascular disease during the study. Probably less than 10 years, maybe a year, who knows, probably more. So that would mean the proportion of men who died was 0.0165, and I'll call that P1 hat. That is my estimator of the proportion of men who would die during this given year period if they have high blood pressure, but would die of cardiovascular disease if they have high blood pressure. Okay. Now, during the same study, they followed 2,676 men, and 21 of who they followed 2,676 men who had low blood pressure, and 21 of them died of cardiovascular disease during this study period. So the sample proportion there is 0.0078. So that's our estimator of the probability of a low blood pressure man dying of cardiovascular disease during this given period of time. Okay. We can then divide the two for a good reason. Okay, so if I divide those two proportions, I get 2.12, which has the interpretation that high blood pressure men are 2.12 times more likely to die of cardiovascular disease during this given time period than low blood pressure men. Okay, and this is just from one sample, right? So I might want to bootstrap it and get sort of a confidence interval for what I think this value is. So we're going to bootstrap this thing. And the way we're going to do it, I'm going to switch over to R soon, but the way we're going to do it is we're going to take those 3,338 people, 55 of whom have died, and I'm going to sample 3,338 of them with replacement. Calculate how many of those resample people died, calculate P1 hat star, and I'm going to take 2,676 people with replacement from my low blood pressure group. Some of those will have died, right? Recalculate my P2 hat star and calculate P1 hat star divided by P2 hat star and store that result. Repeat it 10 to the 4th or 10 to the 5th times, create a sampling distribution of this ratio, okay? And then I can go for the 95% confidence interval, and I can go calculate some bias and some standardized bias to see if this modeling is any good, okay? All right, so I'm going to switch over to R. Again, this is example 5.7. Okay, so here I am in line 320, relative risk example. So first off, I have to generate my data, which is slightly unusual. This is actual data from the study. So what I'm going to do is I'm going to randomly select 55 out of 3,283 people to receive a 1. The rest will be zeros, and 1 will mean dead. Okay. And I'm going to do the same thing with 21 by 2,655. So that's going to be to set the initial sample, right? So just run that. Okay. Now I'm going to set up my bootstrap distribution. I'm going to run it 10 to the 4 times. I'm going to have 3 new vectors. Okay, and I'll explain why as we get there, but I'm going to have the boot vector, boot.rr would be boot dash the ratio. I'm going to have a high proportion vector and a low proportion vector, all of length 10 to the 4th. Now, the high proportion vector is going to record the proportion of high blood pressure people who die in a given resample. Low blood pressure group will determine or record the proportion of low blood pressure people who die from a given resample, etc. All right. So here's the way we're going to do it. I've got this high blood pressure group that's randomly selected 55 of 3,338 people who have died. I'm going to resample 3,338 of them with replacement. I'm going to call that X dot high. Same thing for X dot low for the low blood pressure group. And what I'm going to do is I'm going to take the sum here in line 336. I'm going to take the sum of X dot high. So it's going to add up all the ones in X dot high, which is all the number of deaths in this resample, and divide by 3,338 to get the proportion. Do the same for low dot, X dot low, call that low dot prop. And we're going to take high dot prop and divide by low dot prop to get that. The ratio of those two proportions, and that's what I'm going to record in boot.rr. So let me run that rather lengthy loop. And it's taken a fair bit here, but eventually we'll get there, and I can start recording some values on the board. Wow, still going. Oh, there we go. Okay. So first off, I'm going to calculate the 95 percentile of that boot.rr vector. That's 95%, the boot 95% bootstrap confidence interval for that ratio. All right, and I get 1.2, let's just say 1.3, 1.3, comma, to 3.7. Okay, you should probably record that too in your notes. So that means 95% of the time, high blood pressure men are between 1.3 and 3.7 times more likely to die of cardiovascular disease than low blood pressure men. So if our null hypothesis was that the proportions would be the same, I think we can reject that. There's only a 5%, less than a 5% chance of 0 coming out of this thing, because 0 is not our 95% confidence interval. Sorry, it should have been 1 proportion of high blood pressure men, about a proportion of low blood pressure men. If it was the same, that proportion would be 1. And we see that 1 is not part of this 95% confidence interval. Okay. I don't know that I need the mean, but you can give it to us. And then the standard deviation we do need, and that's 0.6238. So 0.6238. Oh, I do need the mean with my bootstrap. What was that? 2.204. Okay. And I think I'm done with the code. You can click through the rest. You get a really cool scatter plot, and you can puzzle through that. But let's get back to the board here. Okay. So I put in the 95% bootstrap confidence interval for that ratio, and it's 1.3 to 3.7. I'm going to calculate the bootstrap bias now. There was the expected value, the mean of P1 hat star over P2 hat star, 2.204. And then the original value was 2.12. So that bias then gives me, calculator, 204 minus 120 is what, 0.086? Oh boy, I feel scared about that. All right. And then I take that bias and put it right here. And I'm going to standardize it by dividing by the standard error of that bootstrap distribution, which R told me was 0.6238. And definitely need a calculator now. So let's see, 2.204 minus 2.1. Oops, 2.204 minus 2.12 equals 0.084. 0.084 divided by 0.6238 gives me 0.135. And that makes me unhappy because that is greater than 0.02. Okay. All right. So we're seeing something about this bootstrapping simulation process was introducing some bias. And it's introducing a fair bit of bias. So much bias that, in fact, I'm not very confident about the veracity, the truth of this confidence interval. So if you're using this statistical method to try and determine whether P1 hat and P2 hat are the same, if they equal each other, the ratio is 1. 1's not a part of the confidence interval. So you might say, nope, they're not the same. I'm confident, I'm at least 95% confident they're not the same. Well, that value there says there's a lot of bias in this model that led to that confidence interval. So I'm not too confident in the confidence interval. So maybe we should find a different way of running this study and trying to do something from it.